Hello everyone, I'm Tareq Salem, a PhD student affiliated to the University of Côte d'Azur and INRIA. And I'm here today to present our work entitled Towards Inference Delivery Networks, Distributing Machine Learning with Optimality Guarantees. This is a joint work with Gabriele Castellano, Giovanni Neglia, Fabio Pianese, and Andrea Araldo. We first define what we consider as a task. So machine learning task is a request generated by a user to perform inference or prediction based on a pre-trained model. An example of such tasks can be image recognition to recognize objects in an image, or converting a speech sample to a text, or a spam filter, and many more applications. So essentially nowadays, there are two main deployment options for machine learning models. These pre-trained models can be executed at the level of the devices generating the requests. And commonly, these devices have scarce resources where we can only execute simple models with low accuracy. Or we can remotely execute a task at the cloud with a high quality model where we have resource abundance, but unfortunately we pay a high cost due to the latency introduced. So in this work, we propose to integrate machine learning inference in the continuum between the end devices and the cloud. In general, the resources are more available towards the cloud, but at the expense of higher latency. So in inference delivery networks, an allocation strategy consists in two coupled decisions: where to store models and which quality to store. We summarize our contributions as follows. So we present the novel idea of inference delivery networks, and then we frame machine learning allocation ideas as an optimization problem. There is NP-hard, and we propose INFIDA, a distributed online allocation algorithm for IDNs with strong guarantees, even without the assumption on statistical regularity on the requests, and the so-called adversarial setting that we describe more in detail. And we evaluate INFIDA experimentally with a greedy heuristic. We model inference delivery networks as a weighted graph where the different vertices represent computing nodes, and the edges between these computing nodes, their weight represents the round trip latency. And as indicated over here, that the user can generate a request to a given task, and the set of tasks the system can serve is represented by a set of integers. And we have a catalog of pre-trained models that are capable to serve these tasks. Then the decision variable that indicates whether a given model is stored at a given computing node is denoted by X. We define an allocation budget that is potentially different among the different computing nodes, where each model has a different size. Thus, we can directly identify the budget constraints that, in other words, says that whatever allocation that I specify in IDN, I should not surpass the allocation budget of each computing node, where this allocation budget could be the maximum allowable GPU, memory, and so on. So we assume that every node has a predefined routing path towards a suitable repository node that contains, let's say, the highest quality models for every task I. Then a request is determined by the pair consisting from a task and a predefined routing path. Then when serving a request on node PJ using model M, the system experiences a cost that depends on the routing path and the serving path, the serving node within that path, and the model selected to execute this task. So our theoretical results hold under this very general cost model, but to be concrete, we refer to the following simpler model, where this cost is a combination of the round-trip latency up to the serving node and the inference delay of executing model M at the serving node Pj, plus the inaccuracy cost weighted by a trade-off parameter that is configured depending on the application beforehand. And we assume that time is slotted, and at every time slot t, the system receives a batch of requests represented by a variable rt, where a request row is requested rt row times within that slot. And the model has an available capacity L. As illustrated here, a request arrives to an inference delivery network, and then within that routing path, it can be served by any of these available models that have available capacity to serve such requests. Then here there is a distinction to be made between serving and IDNs that is quite different than classical content delivery networks, where serving a request whenever a model is found is suboptimal. As we can see here, if this model is stored in node 1, and I immediately serve requests without checking the model stored at node 2, I am paying a cost that could have been avoided if I was serving with this model that has a lower cost. Thus, I need to prioritize low cost and available models. Because of such prioritization, a cost ordering is required. So a model M at node V that has the kth smallest cost to serve request row, then the service cost is denoted by gamma k row, which is the kth smallest cost. And the amount of servable requests at this quality or at this cost is reflected by the effective capacity, which is the variable z. That depends on the allocation x, where if x is equal to 1, I can serve L requests. So the aggregate cost incurred by the system at time t is given by the following formula, where for every request row, I pay the kth cost multiplied by the number of requests served by the kth ranked model, and multiplied by an indicator variable that is 1 when there are still leftover requests that are needed to be served. And equivalently, our objective is to maximize the allocation gain that is just defined as the cost with the repository allocation only reflected by the variable omega minus the cost with the allocation selected x. We note that the available capacities may change from one time slot to another, and these capacities depend on the request arrival order, the scheduling discipline on the node, on the computing nodes, and the distribution of the requests for other tasks across the different nodes. And as well as the request popularity may change from one time slot to another. So this uncertainty and unpredictable environment, we model it as an adversary that selects both these requests and the available capacities, aiming to harm the performance of our system. So we propose INFIDA to operate in this setting, where each computing node maintains a virtual fractional state, and these fractional states drive the physical cache states through randomized rounding. And the virtual states are updated online in a distributed fashion without requiring global knowledge of the allocation states. And the update mechanism at the level of each node is based on online mirror ascent, which is a generalization of standard gradient ascent. We provide the optimality guarantees of INFIDA in terms of the psi regret, where psi is equal to 1 minus 1 over E. The psi regret is defined as the discounted total gain of the static optimum that knows in advance the sequence of requests and model's capacities, minus the total gain of INFIDA. And we find that the psi regret of INFIDA is in the order of square root of t, where t is the targeted time horizon. There are two things to note from this result, is that the average psi regret goes to 0 when the time horizon is large enough. So we perform on average as well as a psi approximation of the static optimum that knows the sequence of models, capacities, and requests in hindsight. And secondly, psi is the best approximation bound achievable for the problem, assuming that p is not equal to np. For our experimental setup, we generate two traces with two different popularity profiles. The first one being a fixed popularity profile, where we generate requests to tasks according to a Zipfian distribution with a given exponent. And then on the right, we generate a slide-in popularity profile to simulate the adversarial setting, where similarly we generate requests to tasks using a Zipfian distribution, except that we do a cyclic shift on the distribution periodically, as illustrated here. And then for the performance metric of choice, we evaluate the performance of a policy in terms of the average gain normalized to the number of requests per second. In this experiment, we show the effect of the trade-off parameter on the allocation chosen by INFIDA, where for low values of the trade-off parameter, we see that inaccuracy has less importance. Therefore, to minimize the latency, the allocations push more models closer to the user. And when the inaccuracy cost becomes more important as the trade-off parameter is increased, we see that we can no longer push models next to the users, and the requests are being forwarded closer to the are forwarded to the cloud. In this experiment, we evaluate quantitatively the effect of the trade-off parameter on the average latency experienced by the system and the average inaccuracy. As we observe, when we increase the value of the trade-off parameter, the inaccuracy decreases, but at the expense of a higher latency. And then over here, we show the performance of the proposed policy INFIDA compared to a greedy heuristic. And we see that consistently INFIDA provides the highest gains throughout different values of the trade-off parameter. Furthermore, in this experiment, we show the performance of both policies when we increase request loads on the network. On the fixed popularity profile, we observe that INFIDA is consistently robust to this change on request loads, while the greedy heuristic, when we increase the number of requests per second, we see a decrease in performance. And then on the slide-in popularity profile trace, we observe a similar thing, but in addition, we see that the greedy heuristic is affected as well by this popularity change. And INFIDA, similarly to the change of request loads, we see that it's also robust to a change in popularity profile. And this is due to the fact that INFIDA is designed for an adversarial setting. So we arrived to this last slide. Thank you for your attention, and we hope that you enjoyed our presentation.